Swayam Prabha. Digital India. Educated India.
Welcome to the lecture number 2 of NPTEL video course on Geotechnical Earthquake Engineering. Let us see on this slide this NPTEL video course on Geotechnical Earthquake Engineering. We started with lecture number 1 in the previous lecture, and today we are starting our second lecture for this video course. In that course, as we were going through the first module, module number 1, which is Introduction to Geotechnical Earthquake Engineering. Before we start our today's lecture number 2, we will quickly do a recap of what we have learned in our first lecture. So, we have seen the various effects of earthquake, like devastating effects of earthquake due to failure of structures like this, which all of us are aware about. And one thing we have observed or discussed, that earthquake never kills, but the damage of these structures during the earthquake, that finally kills. And why this damage of the structures occurred during an earthquake? Either because of incorrect design and construction or insufficient design and construction during to withstand these earthquake forces. We have also seen the devastating effects of earthquake due to failure of the soil below the structure or in the foundation soil. So, it is not necessarily that the superstructure or the building failure will occur due to the earthquake. It may be the reason given to the behavior of the soil during the earthquake process or the foundation failure. As shown through these slides already, that the superstructure was designed perfectly fine to withstand the earthquake. However, the soil could not withstand that earthquake or the damage of the soil, either in form of liquefaction or the insufficient bearing capacity of the foundation, or combination of them could have occurred, which finally in turn will fail the superstructure, though it was constructed and designed properly to withstand the structure. So, that automatically told us what is the need of learning this course on geotechnical earthquake engineering. Then we have also seen other geotechnical aspects of this earthquake, like slope failure or the landslide and the rock slide, which we have seen during very recent Sikkim 2011 earthquake in India in September 2011. Also, we have seen other effects of earthquake. One of the major effect of earthquake is tsunami. We have seen tsunami is a Japanese word, and its English translation will become harbor wave, and this figure shows the recent tsunami devastating effect which occurred in 2011 in Japan after the Tohoku earthquake in March 2011. So, height of tsunami wave etc., cause of this tsunami etc., can be due to an earthquake, but it is not necessarily that all earthquake in the deep ocean or large water body will always create a tsunami. There are possible conditions which need to be there to form a tsunami wave. Then we have gone through what are the principal types of earthquake damage, and for that the structural damage, which can be either caused by the excessive ground shaking, and this is strongly influenced by local soil conditions. For that we have seen a very good example of Mexico City earthquake, where the original bedrock seismic acceleration was pretty low. So, it was not supposed to make any such damage to the structure, but unfortunately the soil below the city in Mexico was pretty soft in nature, which caused the soil amplification in that location. So, that way the original bedrock acceleration got amplified or increased, which finally destructed all the structure in the Mexico City. So, that large devastation of Mexico City earthquake in 1985 was majorly due to the geotechnical aspects of earthquake engineering. Then we have discussed in the previous lecture about different aspects of earthquake, like ground shaking, liquefaction, landslides, retaining structures failure, and the indirect effect of earthquake like fire hazard and the tsunami. Then we discussed about what are the various factors on which the earthquake damage depends on a particular structure. It depends on major 4 factors, like size of the earthquake. As we know, as the size of earthquake will increase, chances of damage will increase. The distance from the focus of the earthquake to the concerned structure or the site of interest. So, if the distance increases, then chance of earthquake damage will reduce. The properties of the material at the site, that is, at the site what kind of material is existing, local soil condition or rock condition, whether it is a soft soil or steep soil or hard rock or fissured rock, etc., will decide on how much earthquake damage is going to occur at that particular site. Also, the nature of structure which exists in that area, like whether it is a wooden structure or reinforced concrete structure or unreinforced concrete structure or masonry structure or mud house, depending on type of the construction of the structure, the amount of earthquake damage also will depend on. Then we have discussed about the ground shaking. We have seen that frequency is the important parameter which decides that different seismic wave which are generated during an earthquake process, they will have different frequencies of shaking, and various frequencies will cause different behavior of different heights of the building. Like high frequency body wave will shake the low height building or like single story building or 2-storied building more, whereas the low frequency surface waves, they will shake more on the high rise buildings or tall story building. So, the common layman idea that always the tall story buildings are more vulnerable during an earthquake is not always true. It is true only when the input earthquake surface wave which are caused during the release of an earthquake energy, that is having a low value of the frequency, then only the high or tall story buildings are more vulnerable for the damage. Whereas, if it is having the high frequency body waves, then low rise buildings like even a single story building also will be more vulnerable for the destruction due to earthquake. Also, we have seen that intensity of that shaking also depends on type of subsurface material, as I said, like what type of soil, whether it is a loose soil or a steep soil or a rock, depending on that, that intensity also will depend. Also, we have mentioned in the previous lecture that unconsolidated material will amplify, that is the material or the soil which is still unconsolidated or has not consolidated fully yet, they will have a more chance to get amplify this ground shaking than the rock. And buildings respond differently to shaking depending on construction style, that is what style of construction, whether it is a symmetric construction or asymmetric, etc., and what type of materials are used, like whether it is wood or earthen material or unreinforced or reinforced material. Depending on that, the earthquake vulnerability or the more dependency of the damage on these factors will depend on. We have seen in the previous lecture about collapse of buildings, a case study from the Fukui earthquake of Japan, which occurred in 1948. This is the day and date and time with magnitude and epicentral distance of the earthquake, amount of loss of human life and injuries. Then we have seen the collapse of the houses, which was almost 100%, that is all houses got collapsed in the area of in north south direction by 20 kilometer and in east west direction by 10 kilometer of Fukui plain. And the damage to the pile heads were also observed. So, that was the damage to the deep foundations which were monitored. So, this is the picture which we have discussed in the previous lecture about the damages of various pile foundations during this Fukui earthquake of 1948. Coming to today's lecture, we can continue further on this topic, and we can see this picture which shows the total damage of the Bachau in Kutch region of Gujarat after 2001 Bhuj earthquake, and this is the picture of the total destruction of the area, total damage of the houses and buildings etc., in that Bachau region of Kutch in Gujarat in India in 2001 Bhuj earthquake. Then we can discuss further on principal types of earthquake damage. Another important criteria is liquefaction. So, what is liquefaction? Liquefaction mostly occurs in loose saturated sands. In this condition, the grain structure collapses and pore pressure, pore water pressure in the soil, that increases or develops. Automatically it will reduce the effective stress, because we know the total stress equals to effective stress plus pore water pressure, or in the other words, effective stress is nothing but total stress minus pore pressure. So, total stress remaining constant, if pore pressure increases, obviously there will be reduction in the effective stress, because we can see this equation, the very well known effective stress equation of Terzaghi. Effective stress is given by total stress minus pore water pressure. So, if this value of U increases during the earthquake process, what will happen? This sigma dash will decrease when this sigma, that is total stress, remain constant. That is what, once the effective stress of the soil reduces, it can be considered as the liquefaction, either partial or fully, depending on the various criteria which we will discuss later on when we will discuss about the dynamic soil properties and the liquefaction chapter in this course. So, what ultimately what happens, that reduction in the effective stress will reduce the strength and stiffness of the soil. So, finally, that damage, that type of behavior which is known as liquefaction of the soil, will create the damage on the structure constructed on that type of soil, which is prone for liquefaction during an earthquake loading. There are various examples of soil liquefaction related destructions during an earthquake or after earthquake. So, soil liquefaction, termed liquefaction, the strength of the soil is reduced, as we have seen just now. Often it reduces dramatically or very quickly, and to the point where it is unable to support the structures or remain stable. That means, this at full liquefaction, the soil particles will behave like fluid or watery material, which will start flowing. So, in that condition, obviously, whatever structure is constructed on the soil will no longer stand on a soil, but it will stand on a fluid by the conversion of this soil through this full liquefaction process during an earthquake. And that is why obviously, that fluid cannot further take the load of the huge structure which is constructed on it. So, finally, the entire structure will get damaged or destructed or collapsed. So, this is the example of Fukui 1948 earthquake. You can see in this picture, the entire area got collapsed and a huge lateral spreading, or the spreading in this portion has occurred due to the liquefaction failure after the earthquake of the Fukui in 1948 in Japan. This is another picture which shows that a very tall structure like this, which got tilted and shifted like this due to the soil liquefaction of the foundation at this pocket or at this point. Let us take another example of case history of earthquake, which is 1964 Niigata earthquake, which occurred on June 16th on Tuesday in 1964 at the local time of 1:02 p.m. and local magnitude was reported as 7.5, and the reference of this can be obtained from the 1995 Great Hanshin or Kobe earthquake and the 1923 Great Kanto earthquake. So, from these two, this Niigata earthquake also can be correlated, and it was observed by several seismologists, geologists, structural earthquake engineer, geotechnical earthquake engineer to study the behavior of various structures after the Niigata earthquake. The amount of death is mentioned over here, and total burnt and collapse of houses is also listed on this slide. You can see here what are the major damages. Major damages were soil liquefaction. Various locations the soil got liquefied after this earthquake, and as a result the structure which were constructed on this soil as considering as a stable foundation material, as it got liquefied or flowed like a fluid, the bridges etc. collapsed, and fire of the oil storage tanks occurred because this storage tank etc. collapsed, similar to the previous picture what we have discussed just now. So, finally, that caused the fire in the entire area, and remember that fire continued for about 300 hours. So, such a long duration it was continuing. So, that is a indirect, but a very big or great damage of earthquake, which can be considered or should be considered for proper design of the structures in the earthquake prone region. And remember one important thing, this earthquake of Niigata occurred in June 16th, whereas the Tokyo Olympic Games, it was hosted by Japan in the same year 1964 between 10th to 21st of October. So, Japanese researchers, engineers, practitioners, they did an extremely good job to rectify the necessary structures, everything after this great damage of 1964 Niigata earthquake. So, they were fully prepared in the month of October, just after few months of this great Niigata earthquake of 1964, and they could host the Tokyo Olympic Games. You can see in the next slide over here, this is the picture of the collapsed building. This is a very common picture. All of us can see this picture as a cover picture of the book of Geotechnical Earthquake Engineering, written by Stephen L. Kramer, as I have mentioned in the previous lecture, that is one of the most important reference book for this course. So, this is the cover picture of that book, which we are all familiar about, those who have gone through that book or those who have seen that book. This picture shows the collapsed buildings of that Niigata 1964 earthquake, either because of liquefaction failure or bearing failure or combination of that. So, what was the details? Like 340 reinforced concrete buildings were damaged in that Niigata city, and the damage ratio of reinforced concrete building was about 22% compared to the other unreinforced building which were fully damaged. So, you can see in this picture collapsed building Kawagi Shiko apartments due to soil liquefaction, and the accelerometer record at this location at this top of the building recorded as 184 gal unit, and at the base of the building it was recorded as 159 gal. So, this is the type of behavior of a structure, reinforced concrete structure, which was designed perfectly fine by structural engineers, but the problem arises because of the ill behavior or non proper behavior of the soil during earthquake, which was probably not fully taken care of during the construction of this building on this soil. So, the liquefaction as well as the bearing capacity failure was the problem for this damage. Now, let us see the various observations of Niigata earthquake. These are few more case studies we can discuss about, like the liquefaction and other failures of 1964 Niigata earthquake. These are seismic observed records at the basement of that reinforced concrete building. You can see the accelerometer recording, acceleration record in east west. Stop. Outside. Repeat. In this slide, we are showing the Niigata 1964 earthquake, liquefaction and other failures. What are the observations of seismic stations, like seismic observed records, which was recorded at the basement of that RC building. This is the acceleration record, the first picture in the east west direction. This is the y axis, tells us about the acceleration value in centimeter per second square unit, and x axis is the time in second. This second picture shows the acceleration record in north south direction, again acceleration versus time. This third picture shows the velocity record, velocity in centimeter per second unit versus time, and the fourth or last record, it shows the displacement record, that is displacement in centimeter versus time in second. You can see over here the maximum value of the acceleration which has occurred in east west direction as well as in north south direction, which can be seen through this velocity record also, is typically close to about 10 seconds. Whereas, if you see when the soil liquefaction got started, it got started beyond this 10 seconds. That is, once it reached this maximum value, after that the soil liquefaction started. Whereas, they monitored from the case history that the bridge started collapsing during this about 80 seconds or so, between 70 to 90 seconds. That is the time when the bridge started collapsing after the soil liquefaction has occurred. So, there is a few second time lag between the soil liquefaction starts and the collapse occurred of the superstructure, which is quite obvious, because this is the time taken by the soil to fully liquefy, and once it fully liquefies, then the bridge started collapsing. And you can see over here the displacement record, which is nothing but integration of this acceleration record twice, and that gives us the maximum displacement occurring at these locations, which finally causes the damage of the structures constructed on that site on this liquefied soil. Now, let us see another example of historical earthquake, the case study of that through this slide, which is the 1995 Great Hanshin earthquake, or it is popularly known as Kobe earthquake, because it occurred close to the Kobe city in Japan. The date of occurrence of this earthquake was January 17th, which was Tuesday of 1995 at the local time of 5:46 in the early morning AM, and epicenter was at Awaji Island. Depth, fault depth was 14 kilometer, the hypocentral depth from the ground surface, and the magnitude was recorded as 7.2. The number of death and heavy injured and light injured and missing all are reported in the slide over here. Completely destroyed houses about close to a lakh, 1 lakh, you can see huge number of damage, and partially destroyed houses more than a lakh, more than 1 lakh. And collapsed bridge, total 46 bridges got collapsed after this Kobe earthquake, and collapsed or heavily damaged building more than 3,000, and total monetary loss was about 96 billion US dollars. So, before this 2011 great Tohoku earthquake of Japan, this Kobe earthquake of Japan of 1995 was the largest or biggest disasters earthquake which occurred in Japan, with magnitude of 7.2. But remember, the Tohoku earthquake was much more than this magnitude, it was close to about 9.1. So, that Tohoku earthquake, that is why it was much more devastating, though from 1995 to 2011, the seismic design and construction techniques have improved a lot which has been adopted at various parts of the Japan, but still then always we cannot ensure at very, very high magnitude like 9 or 9.1. So that all the structures will stand perfectly fine. So this data, this slide shows the basic data of the Kobe 1995 earthquake. This is acceleration record at the Kobe Ocean Meteorological Observatory. This is the north south direction horizontal acceleration record. This y axis is in gal unit. The Japanese people, they use the gal unit. The typical conversion you can do with this is, if you take 818 gal, will be close to about 0.818 G. So that can be a typical conversion what from a gal unit to SI unit one can do. The second acceleration record shows the east-west direction record of the horizontal acceleration, and the third record shows the vertical acceleration record, acceleration versus time. You can see over here the typical duration of the major earthquake which occurred in Kobe, that was for about 12 seconds. So, it is the starting point, this is the ending point, almost close to ending point you can say, and the maximum value of north south direction horizontal acceleration was 818 gal. In the east west direction, the maximum value was recorded as 617 gal, which is close to 0.617 G, and in the vertical direction it was maximum value recorded as 332 gal, which can be considered typically close to 0.332 G. These are the damages one has observed after that 1995 Great Hanshin Kobe earthquake. You can see over here, this was the abutment foundation, this abutment of the bridge that has moved after the soil liquefaction etc. has occurred over here. You can see the lateral displacement occurred at this site. After the liquefaction, what happens? The soil is no longer a solid material, but behaves like a fluid or watery material. So, obviously, they start flowing from a higher slope to a lower slope, that is higher gradient to lower gradient. So, once they flow out or move out from that place, obviously, entire structure what was constructed on that start moving or collapsing, and that collapse can be both in vertical direction as well as in horizontal direction. So, after this Kobe earthquake, this particular abutment portion of this bridge, they moved horizontally, you can see over here, by about close to 3 meter, 2.9 meter was the horizontal movement. This vertical movement at this location was 1 meter. At this level, the horizontal movement was 1 meter. At this level, the recorded vertical movement was 1.4 meter. Such huge amount of movement in both horizontal and vertical direction was observed. You can see over here, this was the initially together, then after this part liquefied and flown out, the total destruction or vertical movement as well as horizontal movement occurred at this location. You can see, you can compare easily, this is the height of a human being, this is the typical height of a person. Compared to that, see the height of the amount of displacement, the vertical height, which is much more than the height of the human being or a people. So, this huge amount of damage can occur, which was also observed during this 1995 Kobe earthquake in Japan. This is another picture which shows the damage of a bridge. This is the approach bridge, which was completed in the year 1993, and span of the bridge was 52 meter. You can see over here, this is the span of the bridge, and the design seismic coefficient which was used for the design of this bridge was 0.3 G as per their design code of Japan at that time, and Keishan foundation was used for this bridge. But after this Kobe earthquake of Japan in 1995, what happened? This portion of the soil got liquefied, and finally, this abutment or this support sinked into the soil, and finally, everything got collapsed like this. So, this is the Nishinomiya-ko-Osahi bridge after its collapse caused by lateral spreading, as I was mentioning. Once the soil gets liquefied, it starts flowing in the as it flows in the gradient wise for the case of water, for higher to lower gradient the same thing occurs. So, lateral spreading induced soil liquefaction caused the damage of the structure constructed on this site. Next, let us see a picture on the ground surface where the soil liquefaction has occurred. So, this slide shows a picture of the sand boiling, what we call in another term sand boiling or soil boiling or the soil liquefaction. This is the groundwater, the underground water which is close to the ground surface are rushing out or coming out to the surface after the liquefaction takes place at the site. This is the picture which occurred at the Kandla port in Gujarat soon after the Bhuj earthquake in 2001 in India. So, that sand blow in mud flats used for salt production southwest of Kandla port, Gujarat. So, this is the soil boiling or sand boiling due to the liquefaction on the ground surface. Let us see other types of principal earthquake damages like landslide. Landslide is another type of principal damage of earthquake. It can occur either due to the liquefaction or it can occur also in non-liquefied soil, that is even in the rocky slope, that landslide can occur due to the earthquake. So, it is not necessarily it has to be a liquefied soil. If it is a liquefied soil, obviously due to the liquefaction the slope stability failure and the lateral spreading will occur, but also in non-liquefied soil or rock also that landslide can occur due to earthquake. So, this picture shows a landslide due to the earthquake which occurred after 1971 San Fernando earthquake. This is the devastating effect of slope instability due to the earthquake. It has this picture has been taken from ERC library. We can see some more earthquake damages. This is the devastating effect of earthquake damage on the pavement foundation. This was the initial pavement foundation. After the earthquake, the entire thing here got collapsed. This is the picture after the 1960 Chile earthquake. So far in the history, we know that 1960 Chile earthquake is the highest recorded earthquake so far in the world. This is another picture which shows the devastating effect of earthquake by liquefaction induced movement. So, after the liquefaction, the soil or watery soil I should mention has moved out from this location and created these big voids. So, this liquefaction induced movement has occurred at this site after the Niigata earthquake in 1964 in Japan. This is another picture which shows the devastating effect of earthquake by the liquefaction induced bearing capacity failure during Turkey 1999 earthquake. Here also one can notice there is not much damage on the superstructure, but the problem was with the soil liquefaction. That is the reason why geotechnical earthquake engineering needs to be studied properly to understand this problem and to make liquefaction resistant or the earthquake resistant construction of foundations also properly to take care of the local soil conditions. This picture shows the effect of liquefaction or liquefaction related phenomenon, as I have mentioned, which is known as lateral spreading. Lateral spreading is nothing but after the soil gets liquefied, it starts flowing. As it become a fluidic state, it starts flowing from higher slope to a lower slope. So, this is the picture after the soil flown from higher slope to lower slope or higher gradient to lower gradient after the liquefaction occurred at that portion. So, upslope portion of the lateral spread at Gujarat after that 2001 Bhuj earthquake in India. This is the picture. This is another picture which shows the lateral spreading in the soil beneath an embankment, which caused the embankment to pulled apart. You can see this is the initial picture of the embankment. After the soil below this embankment, if it gets liquefied, it pulled apart like this and producing a large crack on the center of the road. You can see This occurred in the Alaska 1964 after the earthquake. This much of total destruction of the embankment occurred, and this is nothing but a again geotechnical earthquake engineering problem. Coming to other form of earthquake destruction like retaining structure failure or retaining wall failure. This is the initial retaining wall. You can see one portion of it got collapsed over here after the 1999 Chichi earthquake in Taiwan. This is the close view of that collapse of that retaining structure or retaining wall after that earthquake. Then liquefied soil, they start exerting higher pressure on the retaining wall. Why? Because when we design a retaining wall, it is supposed to withstand the earth, and as we know, in the active state of earth pressure coefficients are typically less than 1, whereas if the soil starts becoming or behaving like a liquefied material, it is nothing but a fluidic material. So, for that the pressure coefficient or lateral coefficient will be 1, which is much more than the active earth pressure coefficient, which is considered for the design of any retaining wall under active state of earth pressure. So, automatically the liquefied soil starts exerting much higher pressure on the retaining wall, and which can cause finally the retaining wall to tilt or slide if it is not designed properly to withstand that amount of lateral thrust coming from the fluidic soil or the liquefied soil. So, this is the picture of a retaining wall failure after the soil liquefaction. Another picture shows here the increased water pressure which causes collapse of the dam. You can see over here at this portion the dam has been totally collapsed. This is due to the increased water pressure during the earthquake condition. Some more earthquake destructions, that is the destruction of the lifelines due to earthquake. What are the lifelines? We can categorize them into two major categories. One, lifeline which are required for the physical health of human being, and another is required for the economic health of a country or of a place or of a state. So, for this lifeline which are required for the physical health of human being or the society or a mankind are like gas, electric power line, water lines, sewer line, storm drain, data, etc. So, these things should not get damaged due to earthquake. So, these are the lifelines. If any of them got damaged, then we can understand the lifeline of a human being or a society gets also totally affected or damaged. Some other lifeline which are required for the economic health of a country or a location or a city or a state like highways, bridges, ports, etc. So, these also should not get damaged due to earthquake, because again if one or combination of them got damaged, then total economic health of a country get damaged due to the earthquake process. Now, let us discuss about the indirect effect of that earthquake, which we have mentioned initially, that is the fire. That is, the fire is the indirect result of earthquake destruction. You can see in this picture, earthquakes sometimes cause fire due to broken gas lines and contributing to the loss of life and economy. That will be the most disastrous. You can see from these pictures, after the earthquake, the entire city got caught by fire, and that is because of the broken gas lines. The destruction of lifelines and utilities make impossible for the firefighters to reach at that fire start where the fire started, and to that makes the situation more worse. Already the earthquake related damages are there. In addition to that, this fire creates the much more problem in that vicinity. An example of those type of damages of fire related hazard due to earthquake or after earthquake is 1906 San Francisco earthquake in California and in USA, and in 1989 Loma Prieta earthquake again in California and USA. These two are witnessed this kind of fire related destruction soon after the earthquake, in addition to the earthquake destruction. Then another indirect result of earthquake destruction can be called as tsunami. As we have little discussed earlier, let us finally go through this detailed version of what are the type of destruction can occur due to tsunami. The tsunamis can be generated when the sea floor abruptly deforms and there will be a vertical displacement of the overlaying water. So, as I have already mentioned earlier, there must be a vertical movement or vertical displacement of the seabed, which will cause this destruction. This vertical movement of the seabed is necessary to create the tsunami after an earthquake. So, the water above the deformed area is displaced from its equilibrium position due to this vertical shifting of the floor, sea floor. Hence, waves are formed as the displaced water mass, which acts under the influence of gravity. It attempts to regain its equilibrium, because originally it was in equilibrium, and by shifting of that sea floor, that water standing on it got displaced, its equilibrium position has changed. So, it will try to regain or go back to another state of equilibrium, and to do that, what happens, you can see over here in this slide, that tsunami travels at a speed that is related to the water depth, and hence the water depth decreases, the tsunami speed slows down, but the height increases. Why? Because let us see next point, the tsunami's energy flux, the total amount of energy which is getting released due to through this tsunami, which is dependent on both the wave speed and the wave height, that remains nearly constant. So, once the energy flux remains constant in the deep sea, where the tsunami gets generated due to the abrupt deformation of the sea floor in the vertical direction, that creates a very high speed of tsunami, but very less wave height to maintain a particular value of energy flux. So, as that tsunami wave travels from deep sea to close to the shore or close to the boundary of the solid surface, that height increases and speed diminishes or speed slows down, which ultimately makes the energy flux of that tsunami remains constant. So, consequently, as the tsunami's speed diminishes, as it travels into the shallower water, that is close to the shore, its height grows. Because of this effect, a tsunami which is imperceptible at sea. So, sometimes it happens that some tsunami cannot be seen at the deep sea level, because it is not having any particular height, it is having a high speed, but it is not having any perceptible height. So, imperceptible tsunami may grow to a several meter of height or more when they come near to the coast or the shore and can flood the entire area. So, this is the picture which clearly shows how the tsunami wave movement occurs. First, this is the sea floor movement should occur. This displacement, there should be a vertical component of this movement, as I have already mentioned, and that creates the waves over here, and finally, this energy flux has to remain constant. So, at deep sea level there is higher speed of this tsunami, but very less amount of height over this static sea level, but as it travels close towards this coast or the shore, you can see this height increases, but speed reduces. So, speed reduces, the typical tsunami speed is listed over here. At deep sea, where the depth of the water is more than 5000 meter, the speed is about 800 kilometer per hour in the deep water. When the water depth is about close to 1000 meter, then medium depth water, the velocity or speed is about 350 kilometer per hour, whereas in shallow water, that is about 20 meter of water depth where it comes, at that location the tsunami movement speed will be about 50 kilometer per hour in shallow water, but height will be tremendously high, and that can be even few meters. Now, due to the earthquake, what are the geomorphological changes occurred at a place? Let us see the criteria of geomorphological changes. Like geomorphological changes are often caused by an earthquake. What does it mean, geomorphological changes? Like movement of the ground surface, either it can be the vertical or horizontal along the geological fault traces, and the raising or lowering and tilting of the ground surface with related effects on the flow of groundwater. That is, once the ground surface everything got tilted or moved, or somewhere the ground surface has raised, somewhere it has gone down, or somewhere the ground surface got tilted, then at those location automatically the original groundwater table where it was located, either they come up or come down, or change of groundwater table location also will occur. That is nothing but one of the major form of the geomorphological change. An earthquake produces a permanent displacement across the fault. Remember, after the earthquake there is no way that the displacement can be regained or come back to original position. It becomes a permanent displacement at that fault. Once a fault has been produced, then it remains as a weakness within the rock forever, and is the likely location for the future earthquake. That means, whenever there is a movement in a fault, which is of course a permanent movement, that remains forever, that is a fault or weakness in the rock that remains forever, and there is no chance that weakness can be recovered. Moreover, those are weakness points are the future possible locations of the earthquake, because already there is a weakness in the rock. So, whenever the earth's interior energy will try to open up or dissipate, those are the points where it will get their weakness in the rock to get dissipated the energy. So, after many earthquakes, the total displacement on a large fault may build up to many kilometers, like several kilometers. The length of the fault can be several kilometers after several earthquakes, and the length of the fault may propagate for hundreds of kilometers. That is, the width or depth of the fault also can be few kilometers, even the length of the fault also can be few hundreds of kilometers. That big opening can occur, or that big weakness can occur in the rock. Let us see in this slide, which list typical major historical earthquakes around the world. There are of course several other major earthquakes, but it has been listed only some typical major earthquakes all over the world, starting from like 1556 in China. Number of deaths are listed over here, magnitude is listed over here, and then 1906 San Francisco earthquake, the magnitude. South Chile earthquake of 1960 of magnitude 9.5, 1964 Alaska earthquake magnitude 9.2, 1976 China earthquake magnitude 7.8, 1985 Mexico City earthquake, then 1989 Loma Prieta earthquake in California, USA, then 1995 Kobe earthquake in Japan, then 2001 Bhuj earthquake in Gujarat in India, then 2004 Sumatra earthquake of magnitude about 9.1, 2005 Kashmir earthquake or Pakistan and India border earthquake in 7.6, 2008 China earthquake of 7.9, 2010 Haiti earthquake of about 7, 2010 this Haiti earthquake was in January, and 2010 February was Chile earthquake, which was magnitude of 8.8, but Haiti number of deaths and destruction was much more than the Chile earthquake. We will discuss all these things later on in this due course of time for this course. And 2011 Japan earthquake, where of course the destruction was pretty huge, not only due to the earthquake, but more due to the tsunami, and this was the magnitude of the earthquake 9.1. This is another list which shows the some significant earthquake in India and in its neighborhood. You can see various date, latitude, longitude of epicenter, the location of earthquake, various Indian earthquake, and their corresponding magnitudes are shown over here. like 1819 on June 16th, this Kutch Gujarat earthquake, it experienced 8 magnitude earthquake. Then 1869 January 10th, near Assam, there was a magnitude of earthquake 7.5. Then 1885 in Jammu and Kashmir, 7 magnitude earthquake. In 1897 in Shillong Plateau earthquake 8.7. In 1905 Kangra in Himachal Pradesh, magnitude 8. 1918 again in Assam 7.6. 1930 in Dhubri again in Assam in 7.1. 1934 Bihar Nepal border earthquake 8.3. 1941 Andaman Island 8.1. 1943 in Assam again 7.2. 1950 Arunachal Pradesh earthquake 8.5. 1956 Anjar Gujarat earthquake of 7. 1967 Koyna earthquake in Maharashtra 6.5. 1975 in Kinnaur in Himachal Pradesh 6.2. 1988 Manipur earthquake 6.6. Again 1988 Bihar Nepal border earthquake. 1991 Uttarkashi earthquake. Then 1993 Latur earthquake. 1997 Jabalpur earthquake. 1999 Chamoli earthquake and 2001 Bhuj earthquake. After that there are several others earthquake. Latest one, major one was 2011 earthquake in September 2011 at Sikkim earthquake. So, all this data of the earthquake can be obtained from the USGS website as well as IMD of India government website, from where you will get the basic data or basic information about all these date of earthquake, the epicentral locations in terms of latitude and longitude and their magnitude. All these details are available from USGS website, PEER website and IMD website, and there are other several sources for this information. Let us see the historical strong earthquake and damages worldwide till the year 2010. This details are available in the journal paper. If somebody is interested, can go through this journal paper. This is the name of the journal, Structural Longevity, by myself. In 2010 it has been published. It listed all the historical earthquake which caused major damages, like 1687 Peru earthquake of magnitude 8.5. These effects are mentioned over here, like destroyed much of the city. Then 1730 in Chile earthquake, then Portugal earthquake, Chile earthquake again, and so on. Again other earthquake you can see over here, like 2004 December 26 earthquake of Sumatra, that triggered also a tsunami. You can see some of these earthquake caused the tsunami if it's originated in a deep ocean or seabed and with a vertical movement of that seabed. And also you have seen that Chile earthquake of February 2010, that also generated tsunami and number of people killed. Now, I want to mention in this slide that worldwide largest and deadliest earthquake during the year 2000 to 2010. One should remember that it is not necessarily that largest earthquake will be the deadliest one. It is quite obvious, because the largest earthquake is in terms of the magnitude. Now, if that largest earthquake occurs say in a deep ocean or in a desert, where hardly any human being is living, or there is no human inhabitant is staying at that location, then obviously, though the magnitude is high, the number of damage will be very less or almost nil. So, that will not be a deadliest earthquake. So, deadliest earthquake are those which cause maximum number of damages of the structure and which kills maximum number of human being. So, that is called deadliest earthquake. So, that is the reason you can see over here from this slide that in 2010, when we take the example that February 2010 Chile earthquake is the largest earthquake with magnitude 8.8, whereas the deadliest earthquake of 2010 is the Haiti earthquake of January, which magnitude is 7, which is much lower than the Chile earthquake, but in terms of the fatalities and damages it was the maximum. So, that is why the deadliest is different and largest is different, which is easily understandable. Whereas, in 2009 you can see over here like largest earthquake and deadliest earthquake, that also differs. In 2008 largest and deadliest earthquake, they are same. So, obviously, there may be a chance that largest earthquake, if it occurs in a highly populated area, then it can be a deadliest earthquake, of course. Then 2007 also, this is the largest earthquake, but this is the deadliest earthquake, and so on. All the details can again be seen in this journal paper. This is some more details about the largest and deadliest earthquake, which can be seen. From the earthquake record, this is the Richter scale starting from 0 to 10 scale is shown over here. The latest Tohoku, Japan 2011 earthquake is somewhere here 9.1. You can see this is the San Francisco 1906 earthquake, this is the Kobe 1995 earthquake, San Francisco Loma Prieta 1989 earthquake, and several other earthquakes are listed over here. This is the Chile earthquake of 1960, which is so far recorded the highest magnitude earthquake in the world, about 9.5 in the scale. Now, why we should study the geotechnical earthquake engineering or earthquake engineering as such? You can see from this slide that how much is the share of earthquake disaster in the entire 20th century, as given by Welling and Mohanty in 2009. You can see among all the disasters, earthquake takes the share of more than 50%, close to about 51%. Next highest important disaster is flood, which is close to 30%. Next highest disaster is tropical storm, which is about 17%. Next highest disaster is volcanic eruption, which is close to 2%. Next highest disaster is tsunami, which is about 0.5%, and the last one disaster is landslide. So, among all various disaster, earthquake takes the major share, and not only that, if you see the regional share of that earthquake disaster, this pie chart shows here that Asia and Pacific region takes maximum share of more than 85% of the world for this earthquake disaster share, compared to America 7%, Europe 7%, and Africa only 0.5%. So, that automatically shows why we should study the earthquake engineering and geotechnical earthquake engineering in particular. Also in India, where we are from the Asia region, we should more study on this aspect because of the local behavior, local problems on this earthquake disasters, which has been reported through this slide, which occurred in the 20th century. This is a typical picture given by Howe and Bilham in 2005, the relationship between number of fatalities versus earthquake magnitude. You can see the points. Obviously, as we know, earthquake magnitude increases if it is a highly populated area, number of damages or fatalities will increase, but it is not always so. Sometimes you can see with large magnitude, number of fatalities is less. That means probably either the construction was pretty good, design was pretty good, which could take care of that high magnitude of earthquake, or in that locality there was less number of people who were staying at that location. So, with this we have come to the end of module 1 of this geotechnical earthquake engineering video course. We will continue further in the next lecture.